Alright, so in the previous video, we started to look at the principle of relativity, and what we noticed was that if an object is going at a certain velocity and interacts with another object and it changes its velocity, and you're looking at this velocity time in a certain reference frame, say the Earth reference frame, say now then you observe the same interaction in any other inertial reference frame, then what we notice is that even though the velocity values change, the delta V stays the same in any inertial reference frame. Now what does this imply? Where have we seen delta V before? Well, we know that P is mv. We know that P is mv. This is your momentum. So where do you see delta V? Well, delta V is in the change in momentum is m delta V. Okay? So the takeaway message here, and we're going to do a nice example, is that because we've got in any inertial reference frame the delta V is the same, this tells us then that if whatever the delta P, the change in momentum was in the Earth reference frame, that change in P, that delta P, will be the same in any inertial reference frame. What is an inertial reference frame? It's a reference frame that is moving at a constant velocity relative to Earth. Let me just kill my email here. All right, now let's do this example, which will kind of reinforce this idea. Oh, so here it is. Here's what we're trying to see. The change in a system's momentum is the same in any inertial reference frame. So let's have a look at this example, example 6.3. This cart is 0.12 kilograms. I'm not going to go into all the details of the calculations, as always. It's right in front of you. I'm going to hit the main points. So it's a cart, and it's, remember, I want to keep reinforcing this. VEC. What does that mean? It means the cart, the velocity of the cart relative to Earth. Okay, VEC. So it's moving on a straight low friction track. As you can see, it's going at a constant velocity of 0.4, and then it says it gets a shove. Somebody pushes it so that its speed changes. By the way, if there's a cart there and then somebody shoves it, it's a non-isolated system, right? Non-isolated. And what does that mean? It means it interacted with its environment. There was some momentum transfer across the boundary, which means there is a change in velocity. There's a change in its momentum. Okay, so it's going at 0.4. There was a shove, all right, and it changed to 0.8. Very good. This is in the Earth reference frame, velocity of the cart relative to the Earth, velocity time. Very good. So the question is, determine the change in the cart's momentum as seen from the Earth reference frame. Okay, we've been doing this for millions of years. This is a very easy problem. It's the mv at this state minus the mv over there. Mass times velocity final minus, what did I say? Mass times velocity final minus mass times velocity initial. That's your delta P, right? So the velocity here is 0.8. The velocity there is 0.4. And if you do this, you would get you would get 0.8 times the mass, that's this, and you would get 0.4 times the mass, the inertia, you would get this. You would subtract the final momentum from the initial one, and you would get 0.048 in the in the Earth reference frame. Okay, there's nothing new there. You've been doing that a long time. Now, what about calculating the momentum in another reference frame called M? But this reference frame is moving in the same direction as the cart. So it's moving along with the cart, but at a speed 0.6 meters per second relative to the track. So what is actually happening is that if the cart is moving at 0.4, this reference frame is moving at 0.6. So if you're moving at 0.6 meters per second and the cart is moving at 0.4 meters per second, what do you perceive the cart to be doing? Well, the cart is moving at a negative 0.2 to you. Does that make sense? Guys, I want to just remind you of this golden equation. Velocity of the cart relative to Earth is equal to the velocity of the M reference frame relative to the Earth plus the velocity of the cart relative to the M reference frame. Okay, we saw this already in 6.2, I think. 6.2, we were introduced to this. Okay, so the velocity of the cart relative to Earth is equal to this. It is equal to the relative velocity of the reference frames plus the velocity of the cart relative to the M reference frame. So what are we trying to do here? We are now trying to find the velocity of the cart in the new reference frame. That's what we're trying to do. We already have it in the Earth reference frame, but we're trying to find it in the new reference frame. So what do we need to do? We need to subtract the velocity of the M reference frame relative to Earth from the Earth this over here. So it's going to be VEC. So it's the velocity of the cart in the Earth reference frame minus the velocity of the M reference frame relative to Earth will give us our VMC, our cart in the new reference frame. So let's do a quick example. If it was going at 0.4 in the Earth reference frame, I now need to subtract the velocity of the M reference frame relative to Earth, which is, remember, it's plus 0.6, right? If the cart was going in that direction at 0.4, then this M reference frame was moving at 0.6. So it's plus. So I need to minus plus 0.6. Does that make sense? Because if it was going in that direction at minus 0.6, then I would go minus 0.6. Okay, so this is now V. And so what is this initial value in the new reference frame? It is 0.4 minus 0.6, so it's minus 0.2 meters per second. So that's, as you can see, this now gets converted to minus 0.2. And if you do the same thing for the 0.8, you'll see that the 0.8 gets converted to plus 0.2. So this is now my new velocity time curve in my M reference frame. Remember, it's the reference frame that's going at 0.6 and watching what's happening. Okay, but now what was the question? The question was, what is the momentum in this new reference frame? Or rather, the change in momentum. So what do? You calculate MV here, you calculate MV there, and the final MV minus the initial MV gives you your change in momentum. So you go through this and you calculate it. There's my mass, there's my velocity, initial. There is my final velocity and my inertia. Calculate your momentum. Final minus initial gives you 0.048. It is exactly the same as the change in momentum in my Earth reference frame. So this is what we need to take away. The momentum change is the same in the two reference frames. As long as this reference frame is inertial, the change will be the same. Okay? Let's see here in reference frame M, the velocity time curve shifts up or down, right? Can you see this curve? All that has happened in this curve is that it's shifted down so that your zero axis, or your time axis is over there. But its shape does not change. The shape does not change, and therefore the values of delta V and delta P must also remain the same. Good.